the idea behind inverse matrices is that in the first place they act like multiplicative inverse. If you take a look for the numbers, 5 times 1/5 or 1/5 times 5 equals to 1, we can actually do a similar idea with the matrices. It has to be a square, n by n, 2 by 2 or 3 by 3 matrix. And not all matrices have inverse. For example, the ones have determinant equal to 0. It's similar to a number 0. They do not actually have inverses. However, those that do, this would be actually true. That A times A inverse and vice versa, which is a lot of times it's not true if you switch the order with the matrices, but this time you can, and we get identity matrix, which for the matrices, we have ones on the diagonal and zeros everywhere else, on the diagonal from the left hand side to the right hand side. For example, if you're given two matrices, we can actually multiply them to give an identity matrix right here, and if we switch order, hopefully we also get the identity matrix. So they would be inverses if this is true in both cases, which looks like for these two, yes, we do get an identity matrix, so we get inverse. They're both actually inverse matrices. Often, a lot of times, inverse matrices involve fractions. For example, if we see something like this, we can actually distribute 1/2. So some of them we get fractions, and others we can actually simplify. But that's what happens. Now, to find an actual inverse matrix, we have to either do the sort of Jordan-Gauss elimination, like you have seen in homework for 8.1. Here we can actually go to the row operations. The idea is you take your matrix, you pair it right next to the identity matrix right here. And what we're trying to do is we're trying to do the row operation so that over here we get an identity matrix, which is sort of like the reduced row echelon form. And on the other side, we're actually going to get an inverse matrix if possible. So notice how 2 here in the first place, we want it actually to be a 1. So it might be a good idea to switch 2 rows because here we have a 1. And that's what we do right here. And we do the same thing on the other side also. The next idea, once this is a 1, we want to make everything underneath it 0. That's a lot of times is the idea. So we try to make it 0 by the following row operation. And so we get this. Then we're trying to make this entry 1, which is here's the row operation, -1, 6. And then we can actually work backwards. We can try to actually use the row 2 to make this one a 0. And what happens is now we have the identity matrix over here, and what we have here is the inverse matrix. And that's what happens. Now there is a shortcut for 2 by 2 matrices, so we actually don't have to do that. Here is the shortcut, and in fact I do check, so it's 1 over determinant, so that's why it cannot be 0. And we can actually switch the the elements across the diagonal, and change the sign on the elements not on the diagonal. So here is what we get, and it's actually the same thing, so yes, it does work, which is amazing. We can also compute inverses on the calculator, which hopefully I'll make another video. There is a matrix menu on your calculator, which is amazing that we can do that. Here's the idea. This wasn't too bad actually with a 3 by 3. So the idea is kind of, again, we want to make the entry 1, then make zeros everything below it, then the next entry make it a 1, then you want to make 0 for this one, and then there would be the third one. So here's the idea. We'll make it 0 and make this one into a 1. Then we'll work backwards to make these. Using row 3, we can make this one 0 and this one 0 with the appropriate row operations. And finally, we use row 2 with this 1 to make this 6 into a 0. So luckily, we don't encounter fractions here. Otherwise, this method could be quite time-consuming. So here is the inverse matrix. There is a way to do it on your calculator, so look for either another video and inverse matrix method for the next section.